Hello, quick video on circles and points and chords of circles at A level. The useful thing about circles is they allow us to practice finding intersections of curves and lines, and this is going to be useful working backwards from trajectories to find orbits and centres. It will allow us to practice creating equations by solving quadratics and linear equations algebraically, or we can even do some construction geometric solutions to these problems as well by looking at circles. So let's work our way through this then. Okay, let's say that we're told the circle goes through 2 points here. I've marked them in yellow, point 1 and point 2, yeah? Okay, and that they're on a circle. Then we can see that we can draw a line between the two, and we know that both of these points are equidistant from the center, which is a radius r. And so what we can see here is that we have an isosceles triangle. That's the first part, and of course we can chop an isosceles triangle in half and get two similar triangles, and they'd be right angled triangles, won't they? So what we can see here, just by looking at the symmetry of the diagram we've just drawn, is actually what we've got here is that the center of the circle is on a line bisector between those 2 points. So we could either do that by constructing our right angled triangles here, or we could do the construction of a line bisector by creating circles off each of the 2 points, finding their intersection and drawing the line between them. So if we know what the radius is, of course we can find the centre as to how far along that line bisector it is. Alternatively, if we had 3 points on a circle, we could create 2 line bisectors and find where they intersect, and that's going to be our centre. So let's have a go at the first one of these. Let's say that we know that this circle goes through the point -2, 6, and on the left and top there, and 5, -1 on the right, and we know that the radius is 5. So we can therefore quickly construct the midpoint, because it's going to be halfway between those two, and we can find that that midpoint is going to be at 1.5, 2.5 as its coordinates. Now that we know where these points are, we can actually find the distance between the top left point and the midpoint, which of course will be the same going the other way, and we could quickly find that was the distance is 3.5 root 2. So in effect what we've got is a little triangle here. The y difference is 3.5, the x difference is 3.5, therefore we've got a 45-degree triangle, haven't we? So that's 3.5 root 2. But in each case, we could go through the process we've just gone through, and effectively using Pythagoras, we can find the length to the midpoint. Now, if we know that the other side of this triangle here is 5, then we can find that length, the third side, using Pythagoras, can't we? So if that's 5 and that one's 3.5 root 2, then this length here we can find from Pythagoras down the bottom there. You can see it down the bottom. The calculation is 1 over root 2. Okay, so now we've found the side lengths. What we would like to know is what direction which these lengths are going in, so that we can find the center point, can't we? Okay, well, if we just look at the vector going, the chord vector going from -2, 6 to 5, -1, we find that we're going in the x direction +7, in the y direction -7. So here we've got a gradient of -1, haven't we? Okay, for the green line here for the chord. Therefore, if we're looking at the line bisector, well, we know it goes through this midpoint, and now we can find a vector for it, and the gradient of that is therefore going to be +1, because it's perpendicular to the green line, isn't it? The red line is perpendicular to the green line, and we know the relationship between perpendicular vectors, so perpendicular lines and their gradients. So we now know that the gradient of our in this case of our line bisector, it is +1 and it goes through the midpoint. And we know the distance down that line that it goes there is 1/√2. And of course what we could do here quite quickly is just draw ourselves a little triangle here, because we actually know it's a 45-degree triangle, don't we? So if the length of this side is the hypotenuse is 1/√2, then the length of each side is a half, or 0.5, isn't it? So the other point just to bear in mind though is there's a point here I've drawn the centre as being below the chord line, but of course there's a second place it can be up the top here, being the same distance above the chord line, and then we have the circle set above the chord line rather than below. Okay, so that means that we can find the centre as being, well, we've got our midpoint of 1.5, 2.5 with its coordinates, and then we're either going to go up or down the centre line, by line bisector, as we calculated earlier. If our little yellow triangle here is a half and a half, so we can either go down a half and a half, or we can go up a half and a half. So that's our distance. So if we go down, we get to 1.2 as a centre, and if we go up, we get to 2, 3 as our centre. So here are our two potential centres, 1, 2, or 2, 3. There you go. Okay, so that's one way of doing it. We could also do it algebraically, couldn't we? Here's our generalized equation for that circle. We know the radius is 5, so we can put our 5 squared here. We just don't know where the centre is. What we do know though is that each of these points satisfies the equation. Therefore we can substitute it in, substitute those values into the general equation above, and we've now got effectively two simultaneous quadratics. Okay, so here I've put in 5, and there's my -1 for this point, and here I've got -2 and 6 for my x and y's there. So I've got two equations now. Now, life does get easier with circles, because if we take the equation 1 and we take away equation 2, all our x squareds and our y squareds are going to cancel out. Because they've both got coefficients of 1, and the 5 squared is going to cancel out as well. So what we find is we get quite a nice linear equation. Here it is. So that's what equation 1 minus equation 2 simplifies a bit further to there, and it ends up with this very simple equation that the y of the centre must equal the x of the centre plus 1. And if you actually look at this, this is the line bisector equation from above. Yeah, so if we went back to our diagram up here, that red line, what we've done is just created the line bisector equation. And then we can take this relationship and plug it back into our one of our equations above. I'm going to use the first one for the point 5 minus 1. So if I now put in where I had my yc, I've replaced it from above here. I've replaced it in the equation 1 with xc plus 1. Now if I just expand out these brackets, so yeah, I've got two nice completed squares there. If I expand the brackets out and simplify everything, bring all the terms together, I end up with this simplified quadratic equation. Excuse me, getting my line in the way. There we go. So actually we know that there are two solutions. We saw that from the graphical option, but here I've got two solutions for where the x value is going to be, and they're going to be the roots of that quadratic. So completing the square, which is what I've done just below through this section here, gives us the fact that x is going to be 1 or 2, and then if we take those two values and substitute them back up into the equation for y at the top here, into that one, we find the y values that go with each of those x coefficients. And so we know that the two centres are either 1, 2 or 2, 3. So that's what we saw before, wasn't it? Okay, let's have a look quickly now at solving the same problem if we just know 3 points. So here's point 1 is our 2 minus 6, let's say, and here's the 5 minus 1 that we had in the previous example. Now let's add a third point, minus 2 as being the third point. Well, we could solve this graphically by constructing the two line bisectors, one between these 2 points here. So that's our one coming down here, isn't it? That's one of them. Or we can find our line bisector of these 2 points here, the lower two, and that will give us this line here. And where they intersect will be our center of our circle. And if we did that construction, we'd get 1, 2 as being our point. Okay, let's go for an algebraic solution. Well, once again, we know the 3 points satisfy the circle equation, general circle equation. We just don't know where the center is or the radius, but we can just substitute the 3 values into the equation, and we've got 3 equations. As we did before, we can take one equation away from the other, and we'll get linear solutions. And as we did taking equation 1 away from equation 2, we got to this first linear. That's the line bisector equation, which I called equation 4 just to use a bit later on. So we got y of the centre is x to the centre plus 1. And if we took the second and third equations, taking the third away from the second, we actually find that our x value disappears altogether as well, our linear x. So we just find ourselves with a simple one, which is that yc equals 2. But in general terms, what we're going to get at this point is simultaneous equations. Linear equations to solve. That's quite nice, isn't it? Simultaneous linear equations. We know how to do that from GCSE, don't we? So in this case, it fell into our hands that yc equals 2, and therefore substituting back into the equations, we can find that xc equals 1. So quite quickly, we found that the coordinates of the centre of the circle were 1, 2, using a lot of our skills. Okay. So let's summarize where we are then. The center and radius of a circle can be found from points on a circle. Geometrically, we can use line bisectors between points and similar triangles to find where the center is. And algebraically, we can do the same thing using simultaneous equations, and if we take one quadratic away from the other quadratic, we will end up with linear equations, and we just solve linear simultaneous. So I hope that's of use, and best of luck.